Okay, everyone, so with this video, we are going to discuss the errors and uncertainty. So in IB chemistry, the main idea that we need to take away with the section called errors and uncertainty is that all measurement has a limit of precision and accuracy, and this must be taken into account when evaluating experimental research. So this is the main idea that we have to take away from this section. So in order to do that, we first have to identify the types of the data. So there are two types of data. They are qualitative and the quantitative data. So understanding the difference between these types is essential when conducting experiments and recording results. And also when you do a lab, you must always consider these two types of the data. First type of the data that we're going to discuss is the qualitative data. And the qualitative data refers to a non-numerical information, means we are referring to something like color, texture, smell, and changes in appearance. And these are recorded using the senses, not instruments. So color we see with our eye, right? Texture we feel it with our hand. And smell we smell it, right? And the changes in appearance, we also see this with our eyes, right? Okay, so you have seen a video, and in this video, you can see that there has been a color change, right? And then titration was happening. So there was your alumni flask with the unknown uh, exit here, and then there was your burette, right? So this is your burette, and this is your flask. And then you were able to observe that there was like some dropping happening. So when this happens, the color change was happening inside of the flask, right? And you probably have wrote it that there was color change. And if you were a little bit detailed, you must have wrote it as colorless to pink. However, this is not the expected observation or the good observation, right? So when you do an observation, you always want to describe what was happening. So we know that the solution that was added to the burette was the base, and the solution that was added to the flask was your exit. Okay, so we can say that as base was added, however, when approaching the endpoint, means when the reaction almost ends, the each after swirling the flask. Okay, so with this sentence, I'm just describing what is happening during the titration, right? And then lastly, I can say at the end point, pink color. Okay, So this is what I'm going to do if I'm making or if I'm writing down the observation for my report. Okay, so I was just describing describing what was happening at the beginning, and then during the reaction, and then lastly at the end, right? So three different steps. Then let's talk about the quantitative data. So quantitative data refers to a numerical information. So any measurement you make is considered as the quantitative data. So it is like they are such as temperature, mass, volume, time, and concentration. And these data are recorded using tools and they can be expressed in numbers with corresponding units. So, and also at this point, I'm going to say that when you're measuring the volume in IB chemistry, milliliter is same as centimeter cube and liter is same as decimeter cube. Means when you have 1 milliliter, this is same as 1 centimeter cube, and when you have 1 liter, this is same as 1 decimeter cube. Okay, so we all have watched the video together, and now you must have two measurements. The first one must be 2.6 milliliter or centimeter cube. Second reading must be 19.2 milliliter or centimeter cube. Okay, so and you must have wrote it like this. However, this is not the proper way of writing your quantitative data. Okay, so here, I wrote an instruction on how to create a table for quantitative data right here. Okay, so now you have two measurements, and but you cannot just write them just like this way. Okay, this is not the proper way of writing down your quantitative data. So when you're writing your quantitative data, you must always, present them in a table that is well structured. Okay, I have an introduction here, right? Introduction how to create a table for quantitative data, but also I'm going to show you how to create the data for this measurement. Okay, so in this case, we are just measuring the volume of the base we used, right? So we can say something like table number 1, and then we have to write the title, volume of base used, okay? And then 2.6 is the initial volume that we had, and 90.2 is the final volume that we had. So what you can do is we can write initial volume used, and then final volume used, and we can also write volume used. Okay, and then we're going to create the columns in the rows like this, and then we do know that the unit is the milliliter, or you can use centimeter cube, so we can write centimeter cube. And if you know your uncertainty, you should write your uncertainty, but we're going to talk about that in next page. So we're just going to skip that for now. And then we know that the first volume that we used is 2.6. We already wrote the unit here, so we don't have to rewrite the unit. And then we know that the final volume we used is 19.2. That means our volume used is 16.6 centimeter cube. And that's how you should present your volume used. Okay, so make sure you read this introduction. The precision in measuring the data. So in science, the precision of the measurement refers to how detailed and repeatable a measurement is. It is shown by the total number of the digits and the decimal places recorded. The more specific the tool, the more precision the measurements. Okay, so tools for precision. So you can use something like graduate cylinder or pipette. Okay, so the most precise tool that we can use to measure a solution is graduate cylinder and pipette. But if we are making a solution, right, in that case, we have to use the flask. Okay, so to make a solution, we have to use always volumetric flask. Okay, so when we are doing an experiment, tools that we use to make solution is different from tools that we use to measure a solution, right? So based on the situation, we have to use different tools to increase the precision, okay, of the measurement. Okay, test number 3. Let's do a question together. So instruction is, which tool is more precise for measuring small volumes? A graduate cylinder with milliliter markings or a pipette with 10 marks per milliliter? Why? Also, what are the advantages of using each? The simple answer is that the pipette is more precise, okay, because it has more graduations per milliliter. So we can say the pipette is more precise because it has more graduations, allowing for finer readings and more consistent volume delivery. Okay, also there's a part where graduate cylinder is actually better for measurement than the pipette. So let's talk about the advantage of using each, right? So when we use graduate cylinder, it's easier and faster to use for general measurements, and then they are good for measuring a range of volumes. So good for measuring the range of volumes. However, with the pipette, uh, it is more accurate and precise for a small consistent volume. So we can say that the pipette is actually more ideal. So this is more ideal for titrations or controlled experiments. Okay. Then now let's talk about the accuracy and precision. So we have been using the word or terminology accuracy and precision, right? So accuracy is like how close a measured value is to the true or accepted value. And precision is like how consistent repeated measurements are, even if they are not close to true value. And these are the definition of the accuracy and precision. Okay. For task number 4, bull's eye. I want you to watch the video by the TED Ed called Accuracy and Precision. Okay, this video is created by TED Ed, so I cannot show you in my video. So you must watch the video using the link I provided. Okay, so what I want to do is that I want to identify these prompts here, uh, either as a precision statement or accuracy statement. It can be very confusing. So I want you to hear me carefully, okay? So the first prompt, it says that after 10 attempts to hit the bull's eye, an archer hits the same place on the tree next to the target. So he attempts to hit the bullseye 10 times. However, the archer keeps hitting the same place on a tree next to the target. So there's no accuracy, right? Because he's trying to hit the target, but he's not able to do it, but next to the tree or next to the target, right? Keep hitting the next to the target. So he has precision. or no accuracy. Then let's look at the next prompt. An archer hits the bullseye on a target. So he hits the bullseye on a target. He only hits once, right? That means we cannot measure the precision, but we can say this is an accuracy statement. Then prompt number 3, a pitcher repeatedly means continuously throw his ball past the batter and hits the catcher. So he continuously throws his ball past the batter and hits the catcher, right? So it means we are not sure where the pitcher is trying to hit. We're not sure. However, we know that this pitcher is keep hitting the catcher. Okay, so it means since we are not sure where the pitcher is trying to hit, this we cannot identify whether there's accuracy or not. However, there's a precision. Okay, then let's look at the last prompt. So it says that a pitcher throws his ball perfectly to the batter, right? This is not repeated, right? This is not repeated action. Means this only happened once. And also, it seems like the pitcher throws his ball perfectly to the batter and then throw his ball to the batter, because it says just perfectly. So it means the goal of this pitcher is better, right? So we can say that this is accuracy. But we cannot say it's precision because it only happened once. Okay? Okay, so now let's talk about the experimental errors. So it is possible to make errors in design and processes of the investigation. And every measurement in science includes some degree of the uncertainty. Okay, there's no exceptions. Let's highlight this part. Even when procedures are followed correctly, these uncertainties are known as experimental errors and they are a natural part of the scientific work. So it is definitely a mistake. However, it's not a bad mistake. It's like, it's mistake that you have to discuss at the end of the investigation. So there are two main types of the experimental errors. Okay, they are random errors and systemic error. Random error is caused by unpredictable or uncontrollable factors that cause results to vary slightly between trials. And systematic error is caused by a consistent flaws in a tool's setup or assumptions that shift our data in one direction. Okay, then let's first discuss the random error. So random errors are caused by small, unpredictable variations in the experiment. They affect how precise your measurements are. Okay, so these random errors affects precisions. Okay, means how consistent your results are, right? And then they are not predictable, and it varies from trial to trial. Okay, and it cannot be eliminated but can be reduced by repeating measurements. Okay, and then also the results, your experimental results may scatter around the true value. Okay, the results. So when you have a random error, your results can be not accurate and not precise, and it can also be accurate but not precise. Okay, so the source of the random error can be instrument limitations. Okay, analog scale precision, right? When you use analog scale, right, there can be error with the precision, right? And then like something like slight differences in measurement techniques, right? So differences in measurement technique, right? And then also it can be environmental fluctuation, so like temperature change. This can be also the reason for the random error. And also it can be a methodological issue, like inconsistency in how an experiment is conducted across trials, right? It is different from the measurement technique. We are just referring to the inconsistencies in how an experiment. And there can be more than this, right? There can be more sources of random error, but these are the like four major ones, right? Okay, so when we estimating the random error, how we estimating random error is different by the instrument type. Okay, so estimating random error means we are estimating the uncertainty. Okay, when you have an analog instrument type, means something like beaker or analog scale or pipette, burette, right? When we have those, we always have to have the smallest scale division, and then we always have to put plus minus in front. So, and then when you're using the digital instrument, something like digital balance, then the smallest unit displayed by the instrument is your uncertainty. So, and you always put the plus minus in front of it. Okay. So don't forget, we are measuring the uncertainty for the random error, right? So we always have to display the plus minus sign in front of your uncertainty. Okay. Okay, so then let's do test number 5 together. So we have to estimate the random error. So here we have a beaker. Beaker is, a analog tool, right? And the type of error in this case is random. The reason is that this is the analog scale or the analog tool gives the error with the precision, right? That means we have instrument limitations. So that's the reason why we have a random error. And uncertainty in this case is, since it marked every 20 centimeter cube, when you have an analog instrument, we have to have the smallest scale division, right? So this speaker has the smallest scale of this speaker is 20 centimeter cube. So uncertainty in this case is plus minus 10 centimeter cube. Okay. Then let's look at this box here. Okay. So we have a digital balance. We have a digital tool, right? So in this case, uh, we might not have any instrument limitations. However, there can be a slight differences in measurement techniques, means it can be uh, affected, our measurement can be affected by the calibration of this digital balance. So in this case, we have a random error. However, in terms of the uncertainty, since it is a digital, right, we have to take the smallest unit displayed by the instruments. So it reads to the 0.01 gram, okay? Then its uncertainty is plus minus 0.01 gram, okay? Then let's talk about the examples of the other random errors. Okay, so slightly shaking while transferring liquid can be a random errors, okay? Fluctuations in digital instrument readings also can be random errors. Then let's talk about the systemic error. So systemic errors are consistent directional errors that occur every time a measurement is taken due to flaws in equipment, calibration, or measurement method. So systemic error affects accuracy, how close results are to the true value. That's accuracy, right? And also the consistent and predictable. And also the systemic errors are consistent and it can be predictable in direction. Okay? and also, not reduced by repeating measurements. Means when you have a random errors, these are reducible by repeating, right? However, systemic errors are not reducible by, repeating measurements. And then it must be corrected by fixing the source. Okay, so when you have systemic errors, the data can be not accurate but precise. Okay, because it's like errors caused by the equipment calibration, right, or measurement method. So whole thing just changes, and then the results also can be accurate and precise. So there are types of this systemic error. It can be caused by the instrumental and the observational, right, and the environmental. So when I say instrumental, that means there is faulty or uncalibrated equipment, so no errors due to the instrument. And then when I say observational systemic error, it means misreading scales the same way each time. So you just make the same mistake every single time. That's the observational error. And also environmental systemic error means that your result is keep getting affected by the external effects like evaporation, humidity, errors due to the wrong assumption. Then the examples of the systemic errors can be calibration errors, misreading the meniscus from above eye level means when we are reading the meniscus, right? Your eye level should be in front of the meniscus to read it properly. That's what that means. A thermometer that consistently reads 2 degrees Celsius low or high, that can be a systemic error. Gas syringe that leaks during the average dryer, that's also systemic error. And liquid evaporating before being measured is also considered as the systemic errors. Okay, then let's summarize everything that we just discussed. Okay, so when you have a random error, it can be caused by the uh, instrument or method, right? And then it affects the precision. And reduced by repetition, yes, random error, we can reduce it by repeating the trials. And then example for this random error can be like, fluctuating balance readings. That can be example. And systemic error is always caused by the faulty calibration, for example, right? Or bias. And then it can affect the accuracy, right? And then can it reduce by the repetition? No. Then example can be misreading all volume readings the same way. So we can conclude that if the method is inconsistent, it's likely a random error. If the method is consistently wrong, it's likely a systemic error. Okay, then let's do task number 7 together. So instruction is given. So with this case, we have to state whether the error in each scenario is a random error or a systemic error. And we have to explain our reasoning. So first scenario, we have a balance with 0.5 gram too heavy every single time. So in this case, we have a systemic error. Because the error is consistent and always in the same direction due to the faulty calibration. Let's look at this scenario number 2, a slight variation in timing with the stopwatch. So in this case, it's random error because we have a human reaction time varies unpredictably with each trial, right? So that's the reason why this is a random error. If you look at this third scenario, a thermometer that always reads 2 degrees Celsius below actual temp. So means this is another systemic error. The reason is the thermometer is consistently inaccurate due to the calibration error. And fourth, air bubbles trapped in a pipette tip during one trial. This is random error because this is one-time inconsistency affecting one trial, right? This is just one-time thing. And then lastly, reading the period from the wrong angle in all trials. So means this is a systematic. Okay, that means the reasoning can be a consistent misreading due to poor technique, observational error. That's the reason why this is the systemic error.